We'll start in 1 minute. Today we'll continue in section 11.11 on Taylor polynomial applications. On Wednesday we were working on this problem. So we have this function f of x. F of x equals the natural log of x. And we're just focusing on the 6th degree Taylor polynomial, t sub 6 of x at a equals 1. And in symbols, this is what the t sub 6 looks like. But now we'll go ahead and replace a with 1 and simplify the coefficients. So t sub 6 of x. So the function f of x is the natural log of x. A is 1, so the first term is the natural log of 1, which is 0, but we'll catch that in the next line. The first derivative of f is 1 over x. Evaluated at a, that's plus 1. And divided by 1 factorial, so it's just 1, and then times the binomial x minus 1 to the first, or just x minus 1. Then the next term, the second derivative of f of x is negative 1 over x squared. Evaluate that at a equals 1. This is negative 1. So we have minus, and then 1 over 2 factorial, which is just 1/2, times x minus 1 to the second. And then the next term, the third derivative of f is 2 over x to the third, evaluated at a equals 1. That's just 2. And then 2 over 3 factorial is just 1/3. So this is plus 1/3 times the binomial x minus 1 to the third. And then the next term involves the fourth derivative of f, which is negative 6 over x to the fourth. Evaluate that at a equals 1. It's just negative 6. And so we're going to have negative 6 over 4 factorial. And that simplifies to minus 1/4 times x minus 1 to the fourth. And then the next term involves the fifth derivative of f, which is 24 over x to the fifth. At a equals 1, that's just 24. But then the coefficient is 24 divided by 5 factorial. And that simplifies to positive 1/5. So we have plus 1/5 times x minus 1 to the fifth. And just one more term, the sixth derivative of f of x is negative 120 over x to the sixth. Evaluate that at a equals 1 is negative 120. The coefficient then is negative 120 over 6 factorial, and that simplifies to negative 1/6. So we just have minus 1/6 times x minus 1 to the sixth. So that is our degree 6 Taylor polynomial that can be used to approximate the natural log of x for values of x near x equals 1. Okay, use this to approximate the natural log of 1.5. Okay, so the natural log of 1.5 is approximately equal to this sixth degree Taylor polynomial evaluated at x equals 1.5. So t sub 6 of 1.5. The natural log of 1 is 0, so we can ignore that. And then when x is 1.5, we have 1 times 1.5 minus 1 is just 0.5. And then minus 1/2 times 0.5 to the second. I'll just write minus 0.5 to the second over 2. And so on. The next term is going to be 0.5 to the third over 3. And then minus 0.5 to the fourth over 4. And then plus 0.5 to the fifth over 5. And finally minus 0.5 to the sixth over 6. Well, that's good enough. But notice 0.5 is 1/2. If we just take it one step further, 0.5 is 1/2. 1/2 squared is 1/4, so minus 1/2 times 1/4 is minus 1/8. And 1/2 to the third is 1/8. 1/8 times 1/3 is 1/24, so this is plus 1/24. 1/2 to the fourth is 1/16, and 1/4 times 1/16 is 1/64, so we have minus 1 over 64. Then the next term, 1/2 to the fifth, is 1 over 32. And 1/5 times 1 over 32 is 1 over 160. And then finally, minus 1/2 to the sixth is 1 over 64. And 1/6 times 1 over 64 is 1 over 384. Okay, so that's another way to look at how to approximate the natural log of 1.5. All right. So suppose for the next part, suppose a function f is equal to its Taylor series at a, and a Taylor polynomial of f at a is going to be used to approximate the function f within a specified threshold of accuracy. So the question is, how is it determined how accurate a particular Taylor polynomial is in its approximation of f at a? So that should be singular, Taylor polynomial. One option is to use Taylor's inequality. So we recall that if a function f is equal to its Taylor series at a, then f of x is equal to the nth degree Taylor polynomial, t sub n of x, plus the remainder, r sub n of x. And so if we subtract the Taylor polynomial from both sides, then the absolute value of the remainder is equal to the absolute value of f of x minus the Taylor polynomial. And Taylor's inequality states that if the n plus first derivative of f is less than or equal to m, whenever x, the absolute value of x minus a, is less than or equal to some real number d, then the absolute value of the remainder is less than this number, the number m divided by n plus 1 factorial times x minus the absolute value of x minus a to the n plus first. For all values of x that satisfy this inequality, the absolute value of x minus a is less than or equal to d. So just a comment about this. This is just the absolute value of x minus a less than or equal to d. That just specifies the interval near a that the x values are being chosen. So the absolute value of x minus a less than or equal to d, we're assuming d is a positive real number. So when we remove the absolute value symbols, we just get this inequality. Negative d is less than or equal to x minus a, which is less than or equal to d. Solve the inequality for x by adding a to all three parts. So the interval is a minus d less than or equal to x, which is less than or equal to a plus d. Okay. So depending upon the function, we'll determine what number d is picked, depending upon the accuracy needed. Okay, we'll use this idea in the next example. Approximate the function f of x equals x to the 2/3 at a equals 1 with a degree 3 Taylor polynomial. And then after we find the degree 3 Taylor polynomial, we'll use Taylor's inequality to estimate the accuracy of that approximation on the interval. The x values will be from 0.8 to 1.2. So this interval, since the degree 3 Taylor polynomial is at a equals 1, then this number a equals 1 should be in that interval. And you can see that that's the case. Just something to note and pay attention to. Okay, to get the degree 3 Taylor polynomial, we need to compute some derivatives. So the first derivative of f is 2/3 times x to the negative 1/3. The second derivative of f of x, this one is negative 2/9 times x to the negative 4/3. And for the degree 3 Taylor polynomial, we need the third derivative of f of x. So this one will be positive 8/27 times x to the negative 7/3. And then a little bit later, when we use the Taylor's inequality, we're going to need the fourth derivative for that. So let's go ahead and find the fourth derivative of f of x. This is negative 56/81 times x to the negative 10/3. Okay, the degree 3 Taylor polynomial at a equals 1. So the first term is f of 1, which is 1 to the 2/3 or 1. And then the next term is the first derivative evaluated at 1 divided by 1 factorial times the binomial x minus 1. So the first derivative of f evaluated at 1 is just 2/3. And we divide this by 1 factorial, so it's just 2/3, and then times the binomial x minus 1 to the first. The next term in the degree 3 Taylor polynomial is the second derivative evaluated at 1 divided by 2 factorial. So negative 2/9 divided by 2 is just negative 1/9. So the coefficient is negative 1/9. And then times x minus 1 to the second. And then finally, the last term, we have the third derivative of f evaluated at 1. That's 8/27 divided by 3 factorial. So we're going to get plus 4/81, and then times x minus 1 to the third. Okay, that is the degree 3 Taylor polynomial. Don't bother expanding it, just leave it in this form. A handy reason for why we want to leave it in this form is because t sub 3 of x is useful for estimating f of x for values of x near 1. So if you pick a number that's close to 1 but not equal to 1, all you have to do is replace x with that number, and then afterwards do the arithmetic. Okay, now we're going to use Taylor's inequality to estimate the accuracy of the approximation. So this is why we need the fourth derivative. So using symbols, then when we apply the Taylor's inequality, we want the absolute value of the fourth derivative evaluated at x, where x comes from this interval 0.8 less than or equal to x less than or equal to 1.2. We want this to be less than or equal to some number m. For values of x that are in that interval from 0.8 to 1.2. Well, we know what the fourth derivative is. So the absolute value of negative 56/81. And instead of writing x to the negative 10/3, I'm going to write that as 1/x to the positive 10/3. And then for x values that come from this interval from 0.8 to 1.2, what's the maximum possible area for that? So remember, when denominators are small, the numbers are big. So since we have x to the 10/3 in the denominator, this will be a maximum when x is the smallest in that interval, 0.8. So for all of the x values in this interval, this will always be less than or equal to 56 over 81 times 0.8 to the 10/3. So I brought my high-powered calculator to compute this. You can go ahead and compute it on a calculator if you have one. So 56 divided by that quantity. Hey, so the number I get is 1.457589. So this is our number m in the Taylor's inequality. Okay, so the other part of Taylor's inequality is the remainder for the degree 3 Taylor polynomial is denoted by r sub 3 of x. And this will be less than or equal to the number m divided by 4 factorial times the absolute value of x minus 1 to the 4th. This is what the Taylor's polynomial applied to this particular case would look like, and also specify where the values of x come from. X is between 0.8 and 1.2. Okay, we know what m is, but we want to pick the x value that will make this as large as possible. So now which value of x from that interval should I pick? So, okay, we got an answer online, which is one of the correct answers. If we pick x to be 1.2, 1.2 minus 1 is 0.2. We could also pick the other endpoint because we have the absolute value of x minus 1. So either of the endpoints, but it's probably more straightforward just to use 1.2. So this will be less than or equal to the number 1.45457589, 4 factorial. Let's see, 4 times 3 times 2, that's 24. And then 1.2 minus 1 is 0.2 to the 4th. And then key that into your calculator. And see what you get. Okay, I get my answer in scientific notation, so I'm going to have to convert it here, count decimal places. That might be enough. So we have these numbers: 96971726, and then 1, 2, 3, 4, 5. So 0.000096 and so on. That's how accurate the third degree Taylor polynomial approximates f of x on the interval from 0.8 to 1.2. So that's a pretty good approximation. Okay, a picture of that. So keep in mind we have the function f of x is x to the 2/3 at a equals 1. And this is the Taylor polynomial, the degree 3 Taylor polynomial. So here's a graph of the two functions together. The green graph, I didn't color this part either red or green. This is where the two functions are close to each other. But f of x equals x to the 2/3 is the green graph. The degree 3 Taylor polynomial is the red graph. And you can see, well, we do know that two functions are exactly the same at x equals 1. But for values of x near 1, the Taylor polynomial is a good approximation of the original function. So to reiterate, the third degree Taylor polynomial t sub 3 of x is very close to f of x for values of x near 1, as you can see in the graph. So this graphing calculator website was not hard to find. I just typed in something like graphing utility or something. And maybe we've used this already before, but all you have to do is go there. You can type in any number of functions and it will automatically graph them for you. All right, let's move on to the next page. So we'll just quickly review what we already know. If f of x is equal to the sum of its Taylor series at a, then this is the f of x is equal to this infinite sum. The coefficients are the nth derivative of f evaluated at a divided by n factorial, and the binomials have the form x minus a to the n. And the function f of x can be approximated by the nth degree Taylor polynomial, which is just the first, well, a maximum of n plus 1 terms in the nth degree Taylor polynomial of f at a. And as we know, if f of x is equal to the limit of the nth degree Taylor polynomials as n approaches infinity, then f of x can be approximated by any of the Taylor polynomials. But the larger the n, the better the approximation. Okay, the Taylor polynomial described above is useful when approximating a function f near a. And then another review of the Taylor's inequality. One way to determine the accuracy that a Taylor polynomial is in approximating a function is to use Taylor's inequality. If the absolute value of the n plus first derivative of x is less than or equal to m for values of x that satisfy this absolute value inequality, then the absolute value of the remainder r sub n of x is less than or equal to m divided by n plus 1 factorial times the absolute value of x minus a to the n plus 1. And we already saw this earlier, but when you expand this absolute value inequality, it's a minus d is less than or equal to x, which is less than or equal to a plus d. Okay, let's look at the next example. So this time, approximate the function f of x equals e to the x squared at a equals 0 with a degree 3 Taylor polynomial. Then use Taylor's inequality to estimate the accuracy of the approximation on this interval from 0 to 0.1. Well, now we compute 4 derivatives. 3 derivatives, the first 3 derivatives will be for the degree 3 Taylor polynomial. And then the 4th derivative will be for the Taylor's inequality estimate. So the first derivative of e to the x squared is 2x times e to the x squared. So this is just an application of the chain rule. You can think of e to the x squared as a composition of 2 functions. And then this is what you get when you apply the chain rule. To find the second derivative, now we have to use the product rule. So this is like a polynomial function of x multiplied by an exponential function of x. So we have to use the product rule. The derivative of 2x is 2, so 2 times e to the x squared, and then plus 2x times the derivative of e to the x squared, which is 2x e to the x squared. So let's simplify that a little bit. We can write it as 2 times e to the x squared plus 4x squared e to the x squared. Okay, then the third derivative first we find the derivative of 2 times e to the 2x. So that will be 2 times 2x times e to the x squared, or 4x times e to the x squared. So I didn't leave myself a lot of space. We have to use the chain rule again. or the product rule and the chain rule. So the derivative of 4x squared is 8x, so 8x times e to the x squared, and then plus 4x squared times the derivative of e to the x squared. So if we just multiply 4x squared times 2x to get 8x to the third times e to the x squared. Two of the terms are like terms that can be combined, so let's go ahead and do that. The third derivative can be written as 12x times e to the x squared plus 8x to the third times e to the x squared. Let's hold off on the fourth derivative for a while. Let's go ahead and find t sub 3 of x. Okay, the first term is f of a, but a is 0, so f of 0 is e to the 0, which is 1. And then the next term is the first derivative evaluated at a equals 0, which is just going to be 0, 2 times 0. I'll go ahead and write it just to fill in the space, and then we'll simplify it in the next step. So 0 over 1 factorial times x minus 0 to the first. Okay, then the second derivative evaluated at x equals 0 is just going to be 2, and then 2 over 2 factorial, and then x minus 0 to the second. Then the third derivative of f evaluated at a equals 0, we get 0 again. So 0 over 3 factorial times x minus 0 to the third. So our degree 3 Taylor polynomial is just going to be 1 plus x squared. So you might object, we refer to t sub 3 of x as the degree 3 Taylor polynomial, but 1 plus x squared is clearly not a degree 3 polynomial. Well, you just have to live with that when some of the coefficients are 0. So this is t sub 3 of x. It's equal to 1 plus x squared. Okay, so the next part, let's use Taylor's inequality to estimate the accuracy of the approximation on that interval. So now we need the fourth derivative, so we might need the full breadth of the page to compute that. So we'll take the derivative of the first term in the third derivative. So the derivative of 12x times e to the x squared is 12 times e to the x squared, and then plus 12x times 2x. So 12x times 2x is 24x squared. times e to the x squared. And then apply the product rule to the next term. The derivative of 8x to the third is 24x to the second, multiplied by e to the x squared. And then plus 8x to the third times 2x, which is plus 16x to the fourth, times e to the x squared. Let's go ahead and simplify it because the two middle terms are like terms. So the fourth derivative is 12 times e to the x squared plus 48x squared times e to the x squared plus 16x to the fourth times e to the x squared. And now we'll look for the largest possible value of the fourth derivative on the interval from 0 to 0.1. So in symbols, the absolute value of the fourth derivative is less than or equal to some number m for values of x in the interval from 0 to 0.1. Okay, so on that interval, what's the largest possible value for m? For which x value will the absolute value of the fourth derivative be a maximum? At 0.1, yeah. Yeah, e to the x squared is an increasing function. And so at the endpoint 0.1, the fourth derivative will be a maximum. The fourth derivative is positive, so the absolute values aren't really necessary. So if we replace every x with 0.1, we get 12 times e to the 0.1 squared is 0.01. So I'll write that down here so we have more room. So 12 times e to the 0.01 and 48 times 0.1 squared. That's the same as 48 over 100, 48 100ths times e to the 0.01, and then plus 16 times 0.1 to the fourth. That's the same as 16 over 10,000, and then times e to the 0.01. Okay, so what comes next? Well, for the degree 3 Taylor polynomial, we want to know what the absolute value of the remainder is, or sub 3 of x. So this is less than or equal to the number m up there divided by 4 factorial times the absolute value of x minus 0, or just the absolute value of x to the fourth. And this is for values of x between 0 and 0.1. And so this will be as large as possible when x is 0.1. We can make this number m a little bit simpler. So we want to go ahead and find the number for this. If we factor e to the 0.01 out of all three terms, so e to the 0.01, and then times 12, 48 divided by 100 is just 0.48. And 16 divided by 10,000 is 0.0016, I think. And then replace x with 0.1, so we have 0.1 to the fourth. And divide it all by 4 factorial, which is just 24. So let's go ahead and key this in and see what this number is. That will tell us how good of an approximation degree 3 Taylor polynomial is on that interval from 0 to 0.1. Okay. Okay, so I get scientific notation again. So 5, 2. So 1, 2, 3. Okay. So that's how close that degree 3 Taylor polynomial approximates f of x equals e to the x squared on that interval from 0 to 0.1. Hey, a picture of that. Hey, so in this one, the green graph is f of x equals e to the x squared. And the red graph is the third degree Taylor polynomial, 1 plus x squared, which is just a parabola, of course. But as you can see, for values of x near 0, it's a pretty good approximation. So if you were to blow that up, I suppose you would be able to see some light between the two graphs, but anyway, so this hopefully will convince you that Taylor polynomials are a good way to approximate more complicated functions. We have less than 2 minutes left, so we won't have time to finish this problem. But on this one, compute the 4 derivatives for the degree 4 Taylor polynomial. And then in this case, a is equal to 0. and see what you come up with. If you're curious to see an answer, you can request one in an email. But I think we'll go ahead and stop for today. Next week, we'll spend the entire week reviewing for the final exam. So go ahead and sign in for attendance.
Can I go over this with you real quick?
Okay.
Maybe in a couple minutes.